So this is a review of crystals. Again, this is not intended to be a substitute for attending a lecture, but I thought I would review some of the basic concepts of what a crystal is in order to help you be able to study and prepare for the exam. Basically, a crystal is a way to think about a small repetitive unit that then tiles space, and we treat it as basically an infinite solid. They're not really infinite. When you start thinking about surfaces, you have surface effects, and that's a whole nother science. But when we talk about a crystal, we treat it as though it's infinite, and we don't think about the surfaces. We represent a crystal in terms of two things: the lattice and the atomic bases. And the lattice is basically the repeat period. So we might have, say, our unit cell be this, and we'll have lattice points. So for example, maybe we have a lattice point at the corner, and that lattice point then spans itself out to one per corner. And we might have a lattice point in the middle. So remember when we talked about the two-dimensional lattices, one of them was the rectangular centered. So these are going to be our lattice points, is what we call them. And if this is our unit cell, that unit cell is the smallest cell that we can have. Then the rest of our crystal is going to be defined according to our lattice vectors. So for example, this would be lattice vector, we'll call that A1. This would be lattice vector A2. And those tell us how to take this unit cell and tile space. So for example, this one might go here. Well, it would go here. And like that. So this, I've taken my unit cell and I've spanned it by A1, and then 2A1. And I can go in the other direction and it'll go over here. So that's minus A1. I can go plus A2. You go plus 2A2. I can go plus A2 plus A1. And you just do that out to plus and minus infinity. The important thing is that each of these cells looks exactly like the unit cell. And what this means is it means that for us, if we start talking about what's happening inside this crystal, we only need to talk about what's happening in the unit cell, and then we say, oh yeah, and it translates out to everywhere else. So that's how we think about a crystal. When we have a unit cell, I'm going to draw this again. Our lattice points I'm drawing in black. There are 14 possible lattices in 3 dimensions, and there are 5 in 2 dimensions. And I handed out a sheet in class that we talked about the 14 three-dimensional Bravais lattice. So let's talk about the unit vectors that we talked about. Traditionally, unit vectors would be described as a sub number. So A1, A2, A3 for 3 dimensions. We would then have angles as well. So for example, we'd have the angle between lattice vector A1 and A2. In 3 dimensions, we have 3 angles. And oftentimes, those angles are given alpha, beta, gamma, but they can also be given in as an alpha with 2 subscripts. So for example, the angle between lattice vector 1 and lattice vector 2 would be described as alpha 1, 2. The angle between lattice vector 2 and 3 would be alpha 2, 3. And the lattice vector between 1 and 3 would be alpha 1, 3. We also have what's called a lattice parameter. And the lattice parameter is basically the magnitude of the lattice vectors. So for example, we have a rectangular lattice here, and traditionally, then this length would be A, and this length would be B. And then if we had, say, a third dimension, we'd have length C. So we would oftentimes talk about A, B, C, and alpha, beta, gamma as our lengths and our angles. So what's important about the lattice points and the atomic basis? Well, the atomic basis, those are the atoms that sit at each lattice parameter. Each lattice parameter, each lattice point. Each lattice point. We oftentimes we call it decorated. We say is decorated with an atomic basis. So for example, we might say our atomic basis is 1 atom. That's the simplest, right? 1. And if you have a 1 atom atomic basis, let's say, let's make it red, then each one of these lattice points, which I had black, well, now those are red. And that would be our 1 atom basis. We could have a 2 atom basis. So for example, we might have something like I'm going to put my little lattice points as small black dots. And let's say I have 1 atom which is red and 1 atom which is blue. Well then, perhaps I might have blue, and let's put the red here. So I've got my lattice point, and the basis is described as a set of vectors. R1, R2. And that basis then is found at every other lattice point. So we have 2 lattice points in this. This is our rectangular centered lattice. So we'd have that point also having a red atom and also having a blue atom. And a red atom over here and a blue atom. Red atom, blue atom, red atom, blue atom. And if you want to think about what this is doing to the crystal, well, let's draw in some other unit cells. So these are our neighboring cells. Okay, and I've got my lattice points. So then at each one of these, I would have a red atom and a blue, red atom, and then the blue atoms, going over to this side. So we've just drawn a crystal and we've shown how it spans, right? Each point where we have a lattice point, say here, we have an atomic basis that tells how the atoms sit about the lattice point. So let's talk about 3 dimensions. I would say the 2 most common lattices for simple metals are going to be the FCC and the BCC lattice, the face-centered cubic and the body-centered cubic. The face-centered cubic is the cube. And we have lattice points on each corner. And then 1 in the center of each face. So take the left face, got 1 in the center, right face, top face, bottom face, front face, back face. So that's our lattice. And again, this is going to span in all directions out to infinity. We have a set of lattice vectors, A1, A2, and it's a right-handed lattice, so A1 cross A2 gives us A3. And those are our lattice vectors. In the case of it being cubic, all 3 have the same magnitude. So the magnitude of A1 equals the magnitude of A2 equals the magnitude of A3. And we call that lattice parameter just A. So that's our lattice parameter for the cubic lattice. And it's a cube, which means that our angles between all of our lattice vectors are 90 degrees. So in the FCC, in the FCC lattice, imagine we have an atomic basis of one atom. And this is the most common in simple metals. For example, gold, copper, lead. These are all FCC crystals. So let's say we have one atom and each atom sits at the lattice point. So I'm going to draw that in red. Okay, so I drew that in. I drew one red atom at each basis, at each lattice point. How many atoms per unit cell? Well, we can count. So we've got 1, 2, 3, 4, 5, 6, 7, 8. We have 8 atoms at each corner. But the atom on each corner is not all inside the unit cell. Only 1/8 of it is, because there's 8 unit cells. So I've got times 1/8 is equal to 1. So we have 1 atom on the corner. Will be 8 of them being shared amongst 8 cells. So 1 atom in total inside of our unit cell. And then each face, we have 1, 2, 3, 4, 5, 6. We have 6 atoms on the face. But if it's sitting on the face, like for example that atom, well, half of that atom is inside and half is outside being shared with this. So that's only half of an atom. We have 6 times 1/2. 3. Together, 4. So we have 4 atoms per FCC unit cell if we have a 1 atom basis. Another one of the very common unit cells is the BCC, or body-centered cubic. The BCC cell so body-centered cubic, again, it's cubic. So we have a cubic unit cell. The lengths of the sides are all the same, so they all have the same lattice parameter A, and they all have right angles. There's 2 lattice points per cube in the BCC. We have 1 lattice point on the corner, and 1 that is in the very center, body-centered. So if we have a crystal, which is a BCC crystal, then it has 1 atom, and that 1 atom will be at the lattice point. So, for example, if we have some red species, we'll have that. You see, okay, how many atoms? Atoms per cube. Notice that we are scaling this per volume. When talking about crystals in general, it's good to have a sense of the units that you're working with. So this is a volume per cubic volume. So we have 8 atoms on the corners, as we had with the FCC, but now we also, and again, those are shared with 8 cells. So we have 8 times 1/8, and then we have 1 atom in the center. That atom in the center is not shared with anyone else. It's in the center. So 1 plus 1, we have 2 atoms per cube. And that is the BCC crystal structure. So lastly, I'd like to talk about a structure that has a 2-atom basis, and that is going to be the sodium chloride rock salt structure. So 2 atoms, sodium and chlorine. The lattice is FCC, but the lattice and the atomic bases together makes the crystal structure. So when a person asks you what the lattice is one of those 14 Bravais lattice. If they ask you what the crystal structure is, it is the lattice plus the atomic basis. And in that case, crystal structure is the rock salt crystal structure. And I don't know where they came from, but I know that historically a lot of these crystals were coming from mineralogy, and people were looking at things. They would have, the corundum structure, or they would have the, cristobalite, and they were based on those mineral patterns. Anyway, let's look at this. So let's draw in our lattice. So I'm going to try to draw this large, so it'll be a little easier to see. So there's our cube, and our cube is going to have a lattice parameter A and 90-degree angles. I'm going to put an X at each lattice point. So I'm going to put an X at each corner of the cube, and then an X on the left and right face, the top and bottom face, and the front and back face. So those are the lattice points in our lattice. And again, remember, this spans space, so we have a neighboring lattice over here, and here, here, here. But this is our cubic unit cell. And now we're going to talk about our basis and atomic basis. And we have sodium chloride. So let me draw the sodium atom as red, and I'll draw the chlorine as green. Now, how do we represent these? Well, we represent these as vectors, and the choice of vectors, the important thing is that the atoms' relative position to each other stays the same, and their orientation relative to the translational lattice vectors is correct. In the case of sodium chloride, we're going to have one atom, and I'm going to put this at the origin, 0, 0, 0. So that's right on the lattice point. And the other is going to be shifted by 1/2 of the lattice parameter. So I'm going to put my chlorine at 1/2, 0, 0. And let me draw my coordinates in. So I'm going to put my coordinates here, and I'll say that is X. I'm going to have Y go into the board, Y, and have Z come up. So again, I have a right-handed coordinate system. Now, I picked to have the sodium sitting at the lattice point. It doesn't have to be. If I wanted to, so let me draw this in. So I'll put one atom here, and the other is shifted by 1/2 in the X direction. Okay, so that's what I've got. It doesn't have to be like that. If I wanted to, I could have offset them so they'd be, centered on the lattice point. Or if I wanted to, you'll see shortly, I could have also put it in the Y the Y or the Z direction. And that has to do with the symmetry of this particular crystal. But for now, just know that you can pick lattice points that are consistent with the structure, and you can move things around as long as you keep them relative to where they should be, relative to each other. So let's fill these in. So I've got a sodium that's going to sit at each of the lattice points. So I'm going to do the 8 corners. So I got 1, 2, 3, 4, 5, 6, 7, 8. And now I'm going to do the faces of the crystal. 1, 2, 3, 4, 5, 6. So I did the face, 6 on the face. And now let's put the chlorine in. So the first one I took and I offset by 1/2. So now every other one, I also have an atom which is offset by 1/2. So for example, I go over here, it's offset by 1/2. I have an atom which is sitting here. The atom in the center of the bottom face is offset by 1/2, and that puts an atom here. See, that chlorine atom is then sitting between those 2 sodium. So let's draw the rest of these in now. Let's do the rest of the atoms on the base. And now the middle level. That's kind of interesting. I've got an atom sitting right in the very center of the cube now. Okay, so if we look at this, over here, oops, I don't have everything quite yet. We have this far right face. I've got every other atom being sodium and chlorine, right? So I've got chlorine, sodium, chlorine, sodium, chlorine, sodium. Same thing here. We don't have that on this side. Why is that? Well, that is because we didn't take into account that we have another unit cell over here. So let's draw that in. Well, I'm going to pick a different color. Let's draw that unit cell in purple. Okay, there's our cell. Let's draw X's where things should be. Got the corners. Now let's do the faces. Okay, so that's our cell. If we put in our red sodium, that gives us all of our sodiums. And then the chlorine, well, look, that atom in the base center of the neighboring cell, that puts a chlorine here. The atoms in the front and back face of the neighboring cell put atoms here. And the atom in the center of the top of the neighboring cell puts an atom here. So that, I'm going to erase our neighbor. That gives us our sodium chloride unit cell. Let's erase these as well. And there you have it. So sodium chloride, it's FCC. And if you want to look at it this way, the red atoms, they give you the FCC lattice. The green, well, that's also FCC. So it's almost as though you have 2 FCC lattices that are shifted from each other by 1/2. And that's how sometimes people talk about it. another way to think about this is to think about this just in terms of it being periodic. So everything that happens on this face also has to happen on this face. So, before we had those green atoms drawn in, the chlorine atoms, we had them drawn on this face. And we could have just used the rules knowing that, everything that happens over here has to happen over here, and add them on that side. So there's lots of ways to think about this, and mathematically, crystallography is a very interesting field. Okay, we talked quite a bit more in class about crystallography, but this is certainly a review of the content.